Hello everyone, my name is Mohit and today I'm going to talk about Surrogate Module. So in Surrogate Module, we basically have two main classes. First class is SROM, which basically generates reduced order model, and second class is CRIG, which generates meta model response surface, basically which can be used to interpolate data. In order to import this module into your Python script, you can use this command from UQpy import surrogates. So SROM class basically generates reduced order model for random variables or random vectors. As you can see here, SROM class needs a set of samples and attributes of distribution, and it basically generates probability weights associated with each sample. As you can see here, x1, x2, xn, these are the m samples, and the return from SROM class will basically these probability weights. As seen in this figure, for a gamma distribution, you can see you send in like 5 samples and define the attributes of gamma distribution. Return of SRAM class will basically these 5 weights corresponding to each samples. So in order to find out these probability weights, SRAM class basically solve an optimization problem, which basically minimizes the error between marginal distribution, marginal moments, and the correlation between the random variables. So, these are the equation which basically represent our objective function. So let's see how we can use the SRAM class. These are the input attributes of SRAM class. First one is our samples. We need samples to find out the probability weights. Samples can be a list or an n-dimensional array. If it is an n-dimensional array, then rows basically show us the number of samples, and columns are basically the dimension of our input space. CDF target can be a string or a list of string, which basically defines which uses a distribution module to define the cumulative distribution function of our random variables. CDF underscore target underscore parameter are basically the parameters of our CDF cumulative distribution function, and these basically are defined using distribution module. The fourth attribute is basically moments. Moments can be defined using a list or an n-dimensional array. Its size is basically 2 cross the dimension of input space, and basically this if it is an n-dimensional array, then first row is corresponding to first order moment of our random variables, and second row is corresponding to second order moment about origin. And it is a required attribute. There is no default value for that. For the correlation attribute, it basically defines the correlation metric between the random variables, and it is an n-dimensional array. Weights underscore error is basically this alpha term in the optimization in the objective function of our optimization problem, which basically defines the relative importance between the different errors like distribution error or moment errors or correlation errors. Properties is basically a list of booleans which kind of decide which properties you want to include in your objective function. The length of this list is basically 4, and first one is corresponding to distribution, if you want to include the errors in distribution in your objective function or not. Second one is for first order moments. Third element is for the second order moment about origin. Fourth element is for the correlation, and this is the default list for properties. Weight moments, weight distribution, and weight correlation are basically these weights in our objective function, and these are just weight associated with each samples and moments and correlation. And default values for weight moments is basically inverse of moments, which will be defined here. And for weight distribution, default value is n-dimensional array of 1. and weights default value for weights correlation is just an identity matrix. So as I said, the output attribute for the SROM class is the sample weights, which is going to be an dimensional array with size 1 cross the number of samples cross 1. So yeah, you can import SROM class in your Python script using these following commands. You can import surrogate module and then call surrogate.srom, or you can import directly SROM class from UQpy.surrogate. So here is an example folder. You can find example for SROM classes. Here I'm going to introduce you the third example. And so basically in this, there are two parts in this examples. In the first part, I have so for the 3 random variables, which are basically gamma distribution, I have generated the reduced order model for them. And in the second half, I have tried to solve a problem for a 3-story building. If lateral stiffness of each story are randomly distributed, then how we can find out the uncertainty among the eigenvalues of the global stiffness matrix. So you can see here, first I have generated our samples using stratified sampling class, which has been discussed yesterday's session. Then using so STS design here was 3, 3, 3. Basically, then this means I have generated 27 samples in this example, and then I have used SROM class, and I have sent those samples inside SROM class, and I have defined the target distribution here with their moments. You can see the first row of moments are basically the first order moment, and the second row is basically the second order moment about origin. And here weight errors are basically, I have taken 1, 1, 0, which means that I'm not going to consider the correlation here, and just going to see, just going to minimize the error between marginal distribution and marginal moments. And same thing you can see through properties, just distribution errors, first order moment error and second order moment error about origin are considered, and not the correlation now. And so this is the plot for only one of the random variables, which is basically the third one. And you can see this is the actual gamma in orange plot. Basically, it is the actual CDF of gamma distribution, and with only 27 samples which we have generated, and the weights which we have estimated using SROM class, you can see the blue plot shows the approximation from SROM. So now what I have done is that I have defined an Python script which basically takes the input as the 3 values of for a 3-story building, the 3 values corresponding to lateral stiffness of each story. And using those values, first I generate the global stiffness matrix, and then basically this thing identifies the eigenvalue and return the eigenvalues corresponding to each sample. So what I have done is that I have estimated eigenvalues for all the 27 samples, which I already had. And then using Monte Carlo simulation class, which is there in sample method module, I have generated 1,000 samples. And again, I have estimated eigenvalues at those for the samples generated using Monte Carlo simulation. And you can see the plot here for all the 3 eigenvalues. This orange plot basically shows the Monte Carlo simulation approximation for CDF of first eigenvalue using Monte Carlo simulation, and 1,000 samples have been used here. And this blue plot basically shows the CDF of our first eigenvalue using the 27 samples which we have generated using SROM class. And these are the same plots for second eigenvalue and the third eigenvalue. Okay, so let's move on to Krigg class. So Krigg class basically generates a Kriging approximation given a data. So here, if you define set of samples, basically S, and response at those values, that is RY, then Kriging class returns the best linear unbiased predictor. So basically, if we what it does that it defines our it expresses our response as the sum of a regression model and a random function. So this regression model can be in Crig class. This regression, there are three inbuilt regression model, that is constant, linear, and which can be used. And for this random function, this has basically zero mean, and the covariance between two samples can be defined like this, where our sigma is the process variance, and this R is the correlation model. So to use a Crig class, the user have to give the set of data, which is basically the samples and the response at those samples, and user has to define regression model, and this R term basically correlation model. This theta are the hyperparameters, which are estimated using maximum likelihood estimator, and yeah. So these are the attributes for the Crig class samples, which is basically and which is an n-dimensional array or a list. Values are the response of at those samples, which is also n-dimensional array and a list. And these are the required attributes. Same goes for regression model and the correlation model. These should be a string, and there are three regression models inbuilt inside Crig class, which are constant, linear, and quadratic model. For correlation model, there are 6 inbuilt correlation model, that is exponential, Gaussian, linear, cubic, spherical, and spline. Correlation model parameters are basically an n-dimensional array, which defines our hyperparameters in correlation model, and yeah, these are basically this can be either used as the fixed values, or this can be used as initial value for the maximum likelihood estimate problem. And if nothing is defined, then default is defined as ones of dimension 1 cross dimension of input space. And bounds are basically the bounds on it is basically an list which defines the bounds on each hyperparameter, and it is used when we are trying to solve a maximum likelihood problem more than once. Then randomly initial points are generated inside these bounds. OP is just a boolean, which is a default value is so if it is a false, then hyperparameter, though this correlation model parameters will be used as it is as the hyperparameter value, and maximum likelihood problem will not be solved. And if it is true, then optimization problem will be solved to estimate the hyperparameters. Nopt is an integer which basically defines the number of times you want to solve the maximum likelihood problem with a new initial point to estimate the hyperparameters. So as an output, the Crig class gives two methods, basically interpolate and Jacobian. These two are functions basically. Interpolate function can be used to predict response and the mean square error at a new sample point, whereas Jacobian can be used to predict gradient of a model at a new point. If for interpolate method, if we just want the response of the model at a new point, then we just have to send in samples inside interpolate class and we will get the response. If we also want the mean square error, then while calling interpolate class, we have to just define dy equals to true, and it will also return mean square error along with the response. For the Jacobian method, there is only one input, which is samples, and in the samples, and you will get the gradient as an output. So you can import Crig class using these commands. Either you can import surrogate module and then just call surrogates.crig, or you can directly import create class from UQpy.surrogate. So in the example folders, you can see and 3 examples for picking. I'm going to go through the first example. You can go and check the rest of the two. So in this example, basically I have generated our data using stratified sampling class. So it's a one-dimensional case. I have generated 20 samples using gamma distribution, and then I have evaluated function value at those points using run model. And for this example, I have taken a very simple case, which is just a sine function. And once I have defined the samples and I have response at those samples, I can generate our meta model using Greek class, which takes samples. Here, samples equals to x dot samples and values, which are the response at those samples. Then I have used linear regression model here. You can see reg underscore model is equals to linear, and Gaussian correlation model is used in this case. And you can see here n opt is defined as 10. So in order to find the hyperparameters, maximum likelihood has been solved with 10 random initial points. So here is the final result, and you can see here that this blue curve is actually show the actual sine function, and orange curve is output from our grid class. So you can see samples are generated using gamma distribution, where we have dense samples. Kriging approximation is very good, and in the region where we have very sparse samples, Kriging approximation is not that good, but yeah, silver. And using the mean square error, I have defined the 95% confidence interval, which can be seen by this yellow-sided region. And this green curve basically defines the gradient of our sine function, which is basically cos, and which is also accurate in the region where we have more samples. That's it for the surrogate class, surrogate module. Now, I think Louis will continue with the stochastic process. Thank you.